and record it, and I'll post this on D2L and Piazza and whatnot here later today. All right, well, let's go ahead and get started here. First off, we have a limit question. Limit as x goes to infinity of 5 to the x over x to the 5th. So I'm not exactly sure where this came from. It's very possible that this was a web work question or whatnot. But the big thing is, right, actually, this isn't really 6.4. I got kind of a bit ahead of myself. 6.4 is when we start taking the derivatives of this sort of stuff. This actually probably belongs in 6.8. 6.8 is where you have these things, these limits with infinity over infinity. And so this is a good indicator that we need to use L'Hopital's rule on this problem. So we're going to go ahead and apply L'Hopital's rule. And when we use L'Hopital's rule, this is why I originally wrote 6.4, or maybe, I don't remember, maybe whoever put it in the submission said that it was from 6.4 or whatnot. But when you go and you take derivatives, taking the derivative of a general exponential, a to the x, in this case, 5 to the x, this came up in 6.4. And so remember, you're going to have the natural log of the base times a copy of the original function. So the natural log of 5 times 5 to the x. And when you take the derivative of the bottom, we're going to have 5x to the 4th power. Can anyone tell me, maybe in chat here, if I wanted to, well, I guess I'm getting a little bit ahead of myself. This is going to be an infinity over infinity situation yet again. If I wanted to continue doing L'Hopital's rule, can anyone tell me how many times would I have to do L'Hopital's rule in order to get an answer here? Yeah, so something like 4 more times. So like a total of 5 times. That kind of corresponds to this x to the 5th right here, right? But the big thing is that you can see that your denominator is going to be reducing in power, right? In fact, eventually after you do it a bunch more times, right, the 4 is going to come down, and then a 3 is going to come down, and then a 2 is going to come down. And then when you take the derivative of x, right, the derivative of x is going to be 1. So actually this is kind of factorially, right? So once you take this derivative, you know, a total of 5 times, right, you're going to end up with essentially this 5 factorial in the bottom, and then the derivative of x is going to be a constant finally. In the numerator, right, you're just going to keep on getting these natural logs of 5 over and over and over again. But right, this 5 to the x isn't really going to change. You're always going to have a copy of this exponential. So you can do L'Hopital's rule times 4 more times here, or you can just kind of try to think about overall what is this going to look like, right? Your polynomial is going to get smaller and smaller and smaller. Eventually, it's going to be a constant, right? And then your numerator, you just get that exponential, 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 and you're multiplying by this natural log of 5 a whole bunch of times. But now at this point, as x goes to infinity, right, you're going to have infinity on top, right? And then in the bottom, this is just some constant. In fact, it's like 120. If we were to go ahead and multiply through by this 5 times 4 times 3 times 2 times 1, right, you get 120. And well, infinity, and you know, extremely large number divided by anything will still be extremely, extremely large, right? So this is going to be going off towards infinity. So that right there is going to be my final answer, that this limit right here goes to infinity. All right. And I have a question in chat. Could we just use the fact that u to the x is increasing much, much faster than x to the u? I mean, it is a good idea to have some intuition about problems. And that's really good intuition there, that exponentials are much stronger, they increase much faster than polynomials. So whenever you have an exponential like 5 to the x versus a polynomial, no matter what the degree is, x to the 5th, or it could even be x to the 100th power, right? Eventually you're going to take enough derivatives of it and it's going to be constant. And so, yes, that's good intuition there. But of course, if we had something that's like a standard response style question where you do get points for showing your work, you know, I would probably want to see something along these lines. So I guess it probably depends on if this ended up showing up as a multiple choice style question or a standard response style question. Excellent. Well, the next problem that was proposed and I selected here is this integral, the integral of sine x cosine x divided by 1 plus sine to the fourth of x. And I decided for this one, I wasn't going to tell you what section it belongs in. Just because, if you get a problem on the exam, it's very possible that it just says, hey, integrate this thing or evaluate this integral or something along those lines, but it doesn't say what section it's from. And so quite often the difficulty for these integral problems, right, is deciding what to do with them. And by telling you what section it comes from, right, that makes it considerably easier. And so looking at this problem here, I guess, let me maybe pause for second or so. If you would type into chat, what would you do? What would your best guess for this be as far as how to evaluate this? And I just want to see what you guys come up with. All right, so good. We have, looks like the majority of folks, it seems to be kind of split between trig sub and U substitution, right? Trig sub and U substitution. And I would say that, remember for trig sub, like, so I'm kind of more in the favor of maybe a U substitution here. For trig sub was really good when you had especially like square roots of things, right? Because the whole idea with trig sub is that you could then, with a clever substitution, get whatever was on the inside here. So for instance, if you had, the table in 7.3 that was all about this sort of stuff, if you have a square root of x squared plus a squared, if you have the square root of x squared minus a squared, or if you have like the square root of a squared minus x squared. And of course, this can be generalized. You don't need to have a square root necessarily, but that's kind of maybe the inspiration behind trig sub, is that you get to trade in for this perfect square, and then that will nicely cancel with your square root. And so that's why this problem right here doesn't really particularly scream trig sub to me, right? I don't see anything that looks like these things here. And so I do think that this will be in the form of a U substitution, but even then, right, it's not exactly obvious. For instance, if you did the kind of most natural U substitution I would recommend, right, it would be probably U is equal to sine of X. And if you do U is equal to sine of X, you can see that you can get there, but you're actually going to need to have yet another step. So the derivative here is going to be cosine of X, and that's going to nicely take care of this. Oops, and I forgot maybe when I was writing this out to include my dx here. And so you can actually do it this way. It'll take, you're going to need a second U substitution. So maybe you'll call that V or W or something like this. But it turns out to be a little bit faster if you let U be equal to sine squared. And one reason that you may think of doing this is because in your numerator here, you have not only cosine, but you also have sine. And so if you were to take the derivative of this, thinking about my du, right, the 2 would come down. I'd reduce my power by 1. So instead of sine squared, I'd have sine to the first power. Then I would multiply by the derivative of the inside, and the derivative of sine is cosine. And so you can see that we actually have all of this here, sine x and cosine of x. And so we can go ahead and exchange sine x, cosine x, and our dx here for half of a du. So I'm going to go ahead and swap all of that stuff in the numerator here for half of a du, right? Sine x, cosine x, and my dx. And then in the denominator here, well, remember sine squared is my u. And so there's 4 sines in total. So that's going to be u squared, right, in order to get to sine to the fourth. And now this right here, 1 over 1 plus u squared, this should look quite familiar, right? And if not, then you should get out your formula sheet, right? And then you'll really see it on the formula sheet. So on the formula sheet here, this is going to be some tangent inverse. Yeah, exactly. Tangent inverse of u, the 1/2 is going to be along for the ride. And u again was sine squared. Sadly, there's really no way that you can simplify this down and make it any cleaner. The sine squared kind of thwarts that a bit. So that right there is just how I would leave my final answer. All right, let's see what's going on. Yes, thank you. So yes, it would be possible with just u equals sine of x, but you would need to do another u substitution midway through. You would do something like w equals u squared, and that would work out. So yes, this is kind of the fastest way. Hey, buddy. All right. Well, with that, let's go ahead and take a look at my third problem that I've selected, or that was suggested here. I think something like this came up maybe on a quiz or an exam or whatnot. This was one of the main reasons for Taylor series and Maclaurin series. And so it's kind of, maybe it wasn't super surprising that it shows up on a quiz or an exam, right? That we want to find a Maclaurin series for this thing right here. And again, kind of Maclaurin and Taylor series, some of their, you can ask, why do we learn about these things? Why is it useful to take something and turn it into an infinite polynomial? And the answer is that in general, if you just take any old random function, it's very, very difficult to integrate it. Right? Derivatives aren't as painful, I guess, as integrals. And so one thing that Maclaurin series allow us to do is to take some function and turn it into a polynomial, maybe infinite polynomial, right? But then polynomials are very easy to integrate. So while this thing here, right, we don't have a quotient rule, for instance, for integrals or whatnot, by taking this and turning it into a polynomial first, it's going to be very easy to integrate. And then if you're interested in finding like the area under the curve, or if you have some real world problem where this is like a rate of change of something, then you can figure out the accumulated change by using the polynomial. Let's see. I see there's a hand raised here. Ian, you have the floor.
Oh, I'm sorry. What was that thing in the parentheses right there?
Oh, sorry, that's 2t.
Oh, okay.
Yeah, sorry, that's not, oops, not the most beautiful 2t I've ever written. All right, good. So why don't we go ahead and first, well, we're going to integrate here. And of course, we know how to do that with infinite polynomials. But maybe first off, we need to go ahead and kind of look at this integrand a little bit, right? Cosine of 2t minus 1, all divided by t. And so in this case, it doesn't say if I would like to get my final answer in sigma notation or if I just want like the first 4 terms or something. So I'm assuming that it just says like, find the Maclaurin series. So I need to include all of my terms. And so in that case, I'm going to kind of stick with sigma notation. But I think it is really useful to kind of carry around for a little while, at least, maybe the first 4 terms or so, or maybe even just the first 3 terms, just so we can kind of see what this looks like. So, okay, we're going to kind of do 2 things here in one, just to kind of, again, help us visualize this. So first, I need to write down what is the Maclaurin series for cosine, right? So I know this. This is going to be summing up from n equals 0 and beyond. And let's see, we have only the even powers, and it alternates. So alternating only even powers. We're going to have even factorials here. And this is going to be maybe x to the 2n. So that's in the sigma notation. If I wanted to write this out, maybe again, like the first 3 or 4 terms or so, if I plug in n equals 0, I'm going to get 1. Oops, and I did a bad job here. This is what our formula sheet says, but notice that we don't want just cosine of x, right? We want the cosine of 2t. So I should probably go ahead and account for that. And instead of x, I'm going to go ahead and plug in 2t, right? So that's just me kind of, again, looking at the formula sheet. And instead of x, we want 2t. So, okay. If I was to write out the first like couple terms here, n equals 0, we're going to get 1 when we raise a bunch of things to the 0th power here. And then we're going to subtract away. And again, plugging in n equals 1, this would normally be like x squared divided by 2 factorial. But again, instead of x, right, we have 2t. Then we're going to go ahead and add, and this would normally be x to the 4th divided by 4 factorial. So again, you see this alternating piece, and you see the fact that we only have even powers of x, and we only have our even factorials. But again, we're going to be having 2t raised to the 4th power. And maybe I'll just do one more here. 2t raised to the 6th power divided by 6 factorial. And again, this will continue on forever. It's an infinite polynomial. And so now I'm interested in building up my entire integrand here. So I need to subtract off 1, and I need to divide by t. So notice when I subtract off 1 here, if I was to subtract 1, notice that that perfectly matches up with my first term. Remember, this is if I was to plug in n equals 0. This is if I was to plug in n equals 1. This is if I plug in n equals 2. And this is if I plug in n equals 3. And again, it does go on. N needs to go from 0 to infinity, right? So it does go on forever. But notice that 1 perfectly matches up with my first term there. And so when I subtract off 1, one way to do this in sigma notation is just to say, well, cancel out that first term, the n equals 0. Forget about that. And so long as you start at n equals 1 then and go beyond, right? This will perfectly match up with the cosine of 2t minus 1. In preparation for what's coming next, I'm going to go ahead and write this as 2 to the 2n and t to the 2n, right? Whenever you have an exponent here, a couple things multiplied together, right? You can go ahead and distribute that to each piece. So I'm going to do 2 to the 2n and t to the 2n. Because the next thing, after you subtract off 1, you need to divide the entire thing by t. So I've subtracted off by 1, right? And now I need to divide the entire thing by t. So if I was to go ahead and divide this all by t, and I guess I should kind of carry around what I'm actually doing here. So I'm subtracting 1 and I'm dividing by t. Well, we need to take this and we need to divide it by t. And again, maybe if I was to just look at my first couple terms here and divide by t, right? This is going to be 2 squared and t to the first power, right? Because I've divided by t. And then here, this is going to be 2 to the 4th power and t cubed, right? One of the t's goes away because I've, again, divided by t. And maybe one more here, 2 to the 6th power. And so our t is always, right, our power of t is 1 off. It's 1 lower than our power of 2. And that's just because we've divided by t. And so same thing here, if I wanted to kind of simplify down, right? My power of 2's are 2 to the 2n. And if I divide by t, notice that my power needs to go down by 1. So instead of t to the 2n, right, it's always 1 lower than that. So, right, we have t to the first power, t cubed, t to the 5th power, because we're always subtracting off 1 from this. And now we are officially ready to integrate, right? So we've built up our integrand completely. We need to integrate this and evaluate at 0 and x. Of course, when we end up evaluating at 0 inside of a polynomial, right, it's not going to be terribly exciting, right? You're just going to have 0 raised to lots of power. So that's just going to be off 0. So it's going to pretty much look like we're plugging in x a bunch. So let's go ahead, integrate this thing. Oops, there was no integral there. That's why we didn't have the dt. So when I integrate, again, this is where you really see the power of this infinite polynomial, right? Any of your constants, well, they're constants, right? So typically when you integrate things and you have a constant, right, it's just along for the ride. So for instance, this -1 to the n, this 2n factorial, and this 2 to the 2n, those together, right, once you plug in some specific n, right, this is just going to be some constant. So it's along for the ride. And when you integrate with respect to t, right, well, you really need to pay close attention to this, right? And when you integrate, you need to raise your power up by 1. So we're going to have -1 plus 1, or you can just go ahead and cancel these out, and you're going to get t to the 2n. And then you need to divide by your new exponent. Of course, you can always double check and make sure, right? If you take the derivative of this, do you get back to where you started? And the answer is yes, right? Because your power would come down, cancel out with your denominator here, 2n, and you'd reduce your power by 1. So yes, this does kind of line up. It is a good antiderivative, because if you take the derivative of it, you get back to where you started. Now we're going to go ahead and plug in 0 and x. Again, when you plug in 0 into a polynomial, right, it's not going to be doing a whole lot. So we're just mainly going to be plugging in x here. So this is going to be summing up from n equals 1 to infinity, -1 to the n, divided by 2n factorial. We're going to have 2 to the 2n. Might as well put this constant over here as well. We're going to have this extra 2n, and then we're going to have x raised to the 2n, because again, everywhere we see a t, we're plugging in x. We're also plugging in zeros technically and subtracting that away, but when you plug in 0 into all of this, right, you just get 0. So that's why I kind of excluded that. So this right here would be the Maclaurin series for this, right? And of course, if it just asked you for your coefficients, your like C sub n's or whatnot, right? That's your coefficients. A little bit messy, but okay. And then of course, right, we have our variable there, our x's now. So again, this kind of comes from 11.10 or 11.11. Blake, see you have your hand raised. What's going on?
Yeah, why that like every single term is divided by t, but it seems like only one is subtracted by one.
So they all are, right? So instead of t squared, right, we have t to the first, and instead of t to the fourth power, we have t cubed, and instead of t to the sixth power, we have t to the fifth, right? So they all are being subtracted by 1, to account for the fact that we divided by t.
Yeah, but I'm just saying because like you have cosine 2t minus 1, so wouldn't that like every single term is being like has a minus 1 in it now too, since like every single term is being divided by t as well.
Well, as far as the when you like go to evaluate this out, right, plug in n equals 1, right? And if you do that, you should get exactly this right here, right? Because you would get t to the 2 times 1 minus 1. So that would be t to the first power. If you plug in n equals 2, right, you'd have 2 times 2 is 4, minus 1 would be 3. And if you plugged in n equals 3, you would get 2 times 3 is 6, minus 1 would be 5. Does that kind of make sense?
Yeah, I think so. I think I got it.
Okay, super. Good. Let's see, Mark, you also have your hand up. What's going on?
Hi. I just want to see if I have a good understanding of what we did here, because this
Okay.
stuff's always been real tricky for me.
Sure.
So we need to find the Maclaurin series of the integration of its function. So we started with the Maclaurin series of the part of the function we knew, and then step by step manipulated that into our original function, and then just integrated that function that we had.
Exactly.
Okay.
Yeah,
So-
and that's kind of what we did, a fair amount, especially for the nicer problems in 11.10, is that whenever you could use a well-known Maclaurin series to help you build up your function, we found that that was maybe the fastest way, right? It would take a long time, right? If you just use the definition and you took lots of derivatives, right, of this thing here, that would take a while. Right. And so, yeah, anytime that you can use that table of power series in order to help generate this a little bit faster, it's definitely recommended.
Okay. All right. Thank you very much.
Yeah, definitely. All right. And I thought maybe there was one more. Yes, go ahead. You have the floor.
Hello, can you hear
Hi.
me?
Yeah, sure can.
So I just want to make sure the -1 in the function, so cosine of 2t minus 1, that -1 is accounted for by like starting the series at n equals 1, right, instead of n equals 0?
Exactly. Originally for cosine, when you look at the Maclaurin series in our formula sheet, right, it should start off at n equals 0.
Right.
But right, we noticed that when we subtracted by 1, this perfectly aligned with our n equals 0 term, right? So that was kind of this work right here. When we plugged in n equals 0, that was just equal to 1. And so we said, well, since these perfectly cancel out, let's go ahead and simplify that down and just basically exclude our n equals 0 term. And so by starting at n equals 1, you're exactly right. That's where we accounted for that subtraction by 1.
Okay, thank you.
Yeah, no problem. Okay, excellent. Let's take a look at the next one here. So another kind of chapter 11 style question, find the sum of this. And so remember, there's only kind of a handful of situations where we can actually say what an infinite series converges to. And the first time where we saw this was in 11.2 with geometric series. So if you have a geometric series, that we can use this in order to say, right, what a series converges to. And then the other time was with these Maclaurin series, right? So Maclaurin series could help us evaluate out some of these infinite series as well. Otherwise, the rest of chapter 11 was just, does it converge or does it diverge, right? It was just kind of a coin flip to some extent. So yes, with this one right here, this is a geometric series, but it takes a step or so to go ahead and kind of rewrite this to kind of see that. So let me go ahead and do a little bit of algebra here. And I'm going to write this as 2 to the n and divided by 5 to the 2n plus 3 divided by 5 to the 2n. And now I'm going to go ahead and do a couple of things here. I'm going to split up my sum. So I'm going to be summing this and summing and kind of do both of these individually. So this one right here, for instance, I can make this 3 times 1 over 25 to the n. So notice what I did for that second one there. I use this kind of property almost in reverse, right? Normally what we would say is that if you have powers raised to more powers, for instance, like 5 squared raised to the nth power, that you can go ahead and rewrite this and just multiply those exponents together. So you could do 5 to the 2n, right? But in this case, we found that it actually has value because of how our formula is to go ahead and rewrite it in this way, right? Take that 5 to the 2n and rewrite it as 5 squared raised to the nth power. And of course, 5 squared is the same thing as 25. So that's going to help us evaluate that one. Here, we're going to do a very similar trick, but notice that we have 2 raised to the nth power and that 25 raised to the nth power. So we're going to kind of combine these as just 2 25ths, all raised to the nth power. And if you'd like to, right, our formula for the geometric series, again, just as a reminder here, says that if you're summing up a times r to the n, from n equals 0 to infinity, that this is equal to a divided by 1 minus r. So this is going to be our main formula that we're using in order to evaluate this out. And so again, we're trying to get stuff, just one thing for each one of these pieces that's raised to the nth power. That's going to be our r. And then whatever kind of coefficient we have here, that's going to be our a. So all that to say, right, if you'd like to, you can write a 1 right here, just because that's going to be our a for this, right? We can always multiply by 1 and that doesn't change anything. Let's go ahead and include our bounds. And so for this one right here, we're going to have 1 divided by 1 minus 2 25ths. So again, that's my a divided by 1 minus r. For this one right here, maybe you've done so many of these that you're kind of very fast at this now. This is going to be 3 over 1 minus 1 25th. But actually what you're doing here, if we were to slow this down a little bit, we're saying that 1 is the same thing as 1 to the nth power, right? 1 raised to any power is always 1. And so really you're taking these things, 1 to the nth power and 25 to the nth power, and saying, well, we're going to take all of this and raise it to the nth power. So here, now you really see it, right? It really matches our form, this a times r to the n. So our r in this case is 1 25th, and our a is 3 in this case. So we're going to go ahead and sum those two together, and that right there will be our final answer. If you'd like to, you can simplify this down a little bit to make it easier to plug into your calculator, for instance. If this was, I'm imagining this comes up as like a standard response style question. If it's a multiple choice style question, maybe this is just one of the answers, and so you could choose that. So it really depends on what you're trying to do with this. So maybe I'll just show you, right? 1 minus 2 25ths, well, that's going to be 23 25ths left over. And then here, 1 minus 1 25th, you'd have 24 25ths left over. And so when you divide by fractions, that's the same thing as multiplying by the reciprocal. So you could do 25 divided by 23, and you could do 25 divided by 24. And so maybe this would be a little bit easier to plug into your calculator if you'd like. So yeah, this is probably where I'll leave it. All right, so again, the overall story for this is that it's pretty rare for us to be able to say what a infinite series converges to. And so there's only a handful of sections, right? 11.2 and 11.10 where we can really do this. And so you should be looking and trying to think, does this look like a geometric series? Because geometric series, you know, we can actually say what the series converges to. And so that's kind of what gets us into this idea of doing all of this algebra and this rewrite and everything, is to try to make this look like our geometric series, our a times r to the n. So that's kind of what pushed us down this path here. All right. Thank you, Michael, for helping out. I guess the sum is 775 over 184. Thank you. Good. Gabriel, you have your hand raised. What's going on?
So with this problem, if it started at n equals 1 instead of n equals 0, how would we change like our method to figuring out the sum of this problem?
Yeah, so if it starts at a different value rather than 0, then the best way I found to go ahead and account for that is to subtract away something from your final answer. So for instance, let's go ahead and just be reminded what this actually looks like, right? If we were to expand this all out, and if I was to plug in, for instance, n equals 0, well, r to the 0 is going to be 1. So this is just going to be a. And if I plug in n equals 1, right, this is going to be a times r to the first power. And then if I plug in n equals 2, we're going to have a times r squared, right? And we're just going to keep on going forever and ever and ever. And if we add up all of these terms here, this is what gives you the a divided by 1 minus r. So let's suppose that your problem, like you said, has you start not at n equals 0, but n equals 1. So you're really interested in the sum of all of these things. So what we did in class in that case is that we went ahead and pretended that it started off at n equals 0 at first and used this great formula that we had. Once we use this formula, we say, well, how much are we off by? Because obviously we didn't want it to start at n equals 0. It's just that's what our nice formula gives us, you know, an answer for. And we only wanted the sum from n equals 1 and beyond, right? And so we're going to go ahead and rearrange, and we're just going to subtract away this piece right here, our n equals 0 piece. And that will give us the sum from n equals 1 and beyond. So if we want to sum up from n equals 1 and beyond of our a times r to the n, which again is all of this stuff right here, this is going to equal to a divided by 1 minus r. And we're just going to move over our n equals 0 term onto the other side, right? Because this is, again, our n equals 0 term right here. Does that kind of make sense?
Yeah, that makes sense. Thank you.
Super. Yeah, no problem. Good. So I think I have one more question that I went ahead and selected before this began, and then it'll be time for me to go back and kind of see what you guys have submitted as well. So this lives in 7.8. Which is in the world of improper integrals, right? So improper integrals here, and we have the absolute value of x on this interval from -e to e. So remember, improper integrals fall in two different categories, right? The textbook even goes on to name these things. I think they're just type 1 and type 2 improper integrals. And so before, when we had always integrated, right, one of our main conditions that we had is pretty much that you needed a continuous function. And so the big thing with this right here, and maybe it'd be good for us to even draw a picture before we get too far into it, right? If I was to just think about 1 over x. So notice I'm forgetting about the absolute value for the time being. So just 1 over x looks like this. Remember, if I want to have the absolute value, right? The absolute value, well, if you're positive, right, the absolute value doesn't do anything, right? So for instance, if you're outputting like +5 or whatnot, mainly over here, all of our outputs, all of our y values are positive, so they're not going to be changing a whole lot. But for instance, down here, maybe you get out something like -3. And in that case, the absolute value is going to say, hold on a second, we're not allowing negatives here. We're going to take that -3 and make it +3, right? And so the more negative you get, maybe this is like -5 or so, it's going to turn it into a +5. So it actually gets higher and higher and higher, right? And you get something like this. So you almost get sort of this volcano looking thing. So that's what our 1 over the absolute value of x looks like. And again, we're interested in this area from -e to e. So we're interested in what does this area right here sum up to. And so this is where I was kind of talking about, right? That if you don't have a continuous function, in this case, we have an asymptote at x equals 0, then this is one of our cases where you have an improper integral. So because we're integrating across this discontinuity, that's what makes it an improper integral. And so remember, anytime that you're doing an improper integral and you're integrating across a discontinuity, right, you have to kind of break it off and pay close attention at that discontinuity. So for instance, in this case here, instead of just integrating from -e to e of 1 over the absolute value of x, right, we need to break this up and go from maybe -e to 0 of 1 over the absolute value of x, and then go from 0 to e, 1 over the absolute value of x dx. So we need to kind of be very careful about our discontinuities. And the way that we do that is that we kind of break this up and we make sure that we look at those things. If you were to just try to evaluate this, with maybe like the fundamental theorem of calculus or something like this, forgetting that this is an improper integral, well, you would say, well, the integral of 1 over is going to be the natural log, for instance, natural log of the absolute value of x. And then if you were to plug in -e and e, natural log of e is going to be 1. And then you subtract away the natural log of the absolute value of -e is also going to be 1. So you would just say, hey, the area is 0, right? But of course, if we look at this, right, we can very clearly see that the area is not 0. There is some area under the curve there, and it's all positive. So it's some positive area. And so that's why this answer right here is wrong, along with the fact, right, the fundamental theorem of calculus relies on the fact that you have to have a continuous function. So actually the fundamental theorem of calculus, just, hey, take the antiderivative and plug in the endpoints, doesn't work here because, again, you don't have a continuous function. And so on each one of these intervals here, from 0 to e and from -e to 0, right, these are continuous functions, and that's fine. And so you do have to be kind of careful to break it up like this. So I'm going to, for the time being, just try to find the area of this piece. It turns out when you break it up like this and you stare at this very carefully, right, you'll see that this area right here turns out to be infinite. So just by evaluating out this piece, we're going to see that we get a divergent answer, that the answer is that it goes off to infinity. And so if you add even more area to it, this stuff over here, right, it's just going to make it worse. It's, it's going to go to infinity even faster, sort of deal. And so let's go ahead and show that this one right here, that it diverges. So again, on this interval from 0 to e, right, the absolute value is not going to be doing a whole lot. It's already positive. And so when you integrate this 1 over x sort of deal, again, you get the natural log of the absolute value. And when we were doing this in 7.8, remember this lower bound we cut quite often. Again, we're very careful with this. Sometimes, we even saw problems where this alluded to like L'Hopital's rule and things like this, where really you want to take a limit as you get very close to 0, because you can't really plug in 0. You can just talk about a limit as you get very close to 0. So I'm going to go ahead and say that we're integrating from maybe t to r, right? There's no problem at e. It's really just plugging in 0. That's where we have a discontinuity here. And we're going to try the limit as t approaches 0. And technically, we're to the right of this, even though that doesn't particularly matter too much in this case. And so, okay, well, if you plug in e, right, that's not so bad. Again, the natural log of the absolute value of e is just going to be 1. And then you're going to subtract away. And now let's think about, right, the natural log. So here's what our natural log looks like. And if we plug in something that's very, very close to 0, right? We're getting very, very close to zero, right? This is going to be going down towards negative infinity. So this is going to be approaching negative infinity. So we have 1 minus negative infinity. And so, well, minus a negative is going to be the same thing as adding this. And so we can see that this is going to go off towards positive infinity, right? So that this diverges. So this area right here diverges towards infinity. And of course, if you add even more area to this, right, there's a lot of symmetry here. So as you probably guess that the areas ought to be the same. That this will also diverge off towards infinity, right? And so you're going to have infinity plus infinity, a very large number, plus another really large number, that this overall is going to diverge towards infinity. But I would almost guarantee, right, if this showed up as a multiple choice style problem, right, that probably one of the answers is going to be 0, right? If you kind of forget about improper integrals and all that sort of stuff. Of course, one of the answers is going to be that the integral diverges. But you can imagine maybe some of the wrong answers here. One of them could be 0. So again, make sure kind of if you have something where you're trying to integrate over a discontinuity, that you break it up and you kind of pay respect to your discontinuity to some extent. All right. So, okay, we have a raised hand. Good. Mark, you have the floor.
Hi. Would if on the multiple choice and there was an option for just infinity, would that be wrong, or is divergent to infinity and it equaling infinity kind of the same?
Yeah, the overarching one would be that it diverges, right? Anytime that it, your limit of something that doesn't go to a finite value, right? You would say that it diverges. Now, I've seen some problems, though, that it goes on to kind of specify the way in which it diverges, right? So it may say that, for instance, I could imagine that, A equals 0, B equals 1, C equals, I don't know, the 2 natural log of, let's say the natural log of 2 or something like that. D could be that it diverges towards infinity, and E could be that it diverges towards negative infinity, right? So both of these, right, divergent is just the kind of the bin that you put things in when it doesn't go to a finite number. But if you want to have more specificity about how does it diverge, then you could do something like this.
Okay, that makes sense.
Cool. All right, let's see. I saw something just come up in chat. As 1 over the absolute value of x gets closer and closer to the y-axis as x approaches 0 from either side, why doesn't it, the area, approach a specific number? At some point, wouldn't the area being added be so small that it's basically 0? Yeah, and that's one thing that can certainly happen. And that's kind of why you have to be very careful with improper integrals, because, right, as this continues to get higher and higher up, right, you say that, well, I'm adding less and less area. It's kind of to the same extent, right, when you're thinking about adding up in maybe another improper integral sort of way, right? The integral of 1 over x as maybe we go from 1 to infinity, right? So again, here's maybe 1. And if we were to add up all of this area, even though it has infinite length here, again, you're adding smaller and smaller values, right? These heights are getting smaller and smaller. They're getting closer and closer to 0. And yet we know for this, right, that when you add these all up, right, again, this is going to be the natural log of x as we go from 1 to infinity, right, that the natural log of infinity is indeed infinite. And so even though you're adding on smaller and smaller values, it does slowly take you to infinity. You do eventually surpass every finite value. And it's the same thing, right? There's an analog here of summing up 1 over n. Remember, we did this in chapter 11 with the, well, we did this probably multiple times. This is the harmonic series. We also brought up this when we were talking about the integral test or P series and all that sort of stuff. You are adding smaller and smaller amounts, but those amounts do add up and take you past any finite value. So yeah, it's kind of a I agree. The world's strange. All right, so excellent here. Now I'm going to go ahead and peek back at this review session document and just kind of see what's been added, if anything. Okay, we got a couple more here. Let's see, one, maybe a bit of typos. Oh, the convergence. Okay, so we did that. Good. Super. So let's see here. I'm going to go ahead and select a partial fractions question. So remember, partial fractions came up in 7.4. And this one says, I think that this was, oh yeah, so it's a true false question. So yeah, I remember this kind of like from a quiz or exam maybe, that you had something like this in the numerator, and then in the denominator here, you have x squared plus 4 and x plus 3. And this asks, you know, if you were to decompose this with a partial fractions decomposition, again, this is a true false. Let me add true false here. That this looks like ax plus b divided by x squared plus 4 plus c divided by x plus 3. Right, that you can go ahead and decompose this in this sort of fashion here. And this is, as it turns out, that this is false, that you cannot decompose it exactly in this way here with our partial fractions decomposition. Can anyone tell me why not? It's pretty close. It's pretty darn close, but it's not quite exactly right. Gabriel, you have your hand up. Do you have an answer for this or a question?
Yeah, I have an answer. Well, it's just because if you were to like actually like expand, I guess is the right word, like the denominator.
Yeah.
The degree of the numerator will still be bigger than the denominator, which I think with that case you would have to do partial fractions if I'm not mistaken.
Yeah, exactly. So the degree of
Or
the
sorry,
numerator is
not partial fractions, the long division, I believe. I think
Yeah.
that was the method called. Yeah.
Exactly. So the degree of the numerator is 4 and the degree of the denominator is 3. So if your degree of the numerator was smaller or than 3, so if it was a degree 2 or a degree 1 or something like this, this would actually be correct, right? However, in this case, because your degree of the numerator is 4, that means that you're going to have a few extra pieces here. You're going to have some well, I can say with confidence that this is just going to be x here, and then you're going to have some other constant like a d here as well. And so this would be the correct partial fractions decomposition, that you would have a linear term and a constant term, and then you would have all of this other stuff. And so again, it is very close, but ultimately you can't, it's right, this is not equal to that. You can't find an A, B, and C where these would be equal functions. You need to include this bit right here in order for this to all work out. Good. Let me just clean up this Q&A here. So yes, I am recording it and it will be posted. I'm thinking about sprinkling it in D2L under the navigator and in the Piazza probably as well. Michael, saw that you have your hand raised.
Yeah, hey, how's it going today, Professor McCombs?
Oh, it's going pretty good. How about yourself?
I'm doing pretty well. I mean, I had a rough day, but I mean, it's nothing won't get through. But I do have a question about this. Like,
yes,
like why would it be like you know, plus x plus d by itself?
Well, yeah, so I'm using a little bit of extra information because I've done so many of these, right? But the main thing, just like people put in chat, right, is that you need to do long division, that there's going to be some extra pieces that come out of the long division that this is not accounting for. And that's why it's ultimately going to be false. So the fact that it looks like X and D is, again, just because I've done too many of these. But the fact that, again, the big thing is that you need to realize that, yes, you need long division because the degree of the numerator is greater than or equal to really the degree of the denominator. And that's how you would see that they're not equal. Everything else is bonus.
All right.
All right, yeah. Good. So let's go ahead. There's a few, let's see, we did one that was pretty close to that. Well, actually, always good time for a 5.2 style question. Someone asked a 5.2 style question. I think this is the one that, or something similar to it, came up on maybe a quiz or an exam or whatnot. It talks about finding the volume of a solid generated by revolving the region between y equals 0, x equals 2, y equals x squared. So this is how our region is generated about the line y equals 5. And so the first thing that I want to point out is that when you read a question like this, where you need to calculate out the volume of revolution or whatnot, notice how kind of I've written this down is that there, there's a lot of equations with these, and usually they're pretty, dense problems and whatnot. And the main thing that you need to do is kind of separate things into how are you generating your region and how are you rotating it, right? So that's kind of how I've broken this down. So our region here, once we have that, we can go ahead and graph maybe in the XY plane. And so y equals 0 is just going to be the x-axis here. It's all the place where the height is 0. X equals 2 is going to be over here. It's a straight up and down line. Again, there's no restrictions on y with that, but all of our x values must be 2. So, so long as the x value is 2, again, that's going to satisfy x equals 2 here. And then finally, y equals x squared. So that's maybe the most complicated one, but actually, it's not so bad, all things considered. We have something like this, a parabola. And so the only region that is bounded by these three curves is going to be this one right here. Notice that there is another region that touches all three curves, especially if you were to kind of take this out a little bit here, right? This region over here touches all three curves, y equals 0, x equals 2, and y equals x squared. So the key word here is bounded. Right? Bounded means that it's enclosed by the three curves, right? That it doesn't go off to infinity, that it's completely trapped by these three curves. So this is the only region here that is trapped by those three curves. All of the other regions are not trapped. This one would go off to infinity, for instance. And so if you were to, integrate or whatnot, this red area here, right, your volume would be infinite. And so again, the only area enclosed or bounded by the three curves is this one in the green. And now we're going to go ahead and take this. And in order to generate out our solid here, I'm going to cheat using my technology here a little bit. We're going to take that and rotate it about y equals 5. So I'm going to say y equals 5 is up here. So if you'd like to, you can draw a 3D picture. But maybe here I'm going to showcase, if you didn't want to draw out the 3D picture, if you're not good at drawing in 3D or whatnot, how you can still do these sorts of problems. So the first thing is, in order to evaluate a problem like this, we could think about what's on our formula sheet. And on our formula sheet, it says, if you want volume, then you need to integrate area. And it gives you this formula right here, right? Integrate area from whatever, a lower bound to an upper bound, from A to B or something like this. But remember, when we were doing 5.2, we also said that sometimes you can integrate with respect to y. So notice that that is not on our formula sheet. That's one of the things that we have to kind of remember, right? That sometimes you want to integrate with respect to x, and sometimes you want to integrate with respect to y. In this case, because we are rotating about y equals 5, so this really comes down to, that's my eraser. This really comes down to our axis of rotation. Because we're integrating over this horizontal line, or sorry, rotating about this horizontal line, right? We are going to want to integrate with respect to x. So the rule of thumb that we were given, right, is that if you see your axis of rotation is a y equals equation, then you want to integrate with respect to x, right? You want to do the opposite. And likewise, if you're rotating about an x equals something, then you want to integrate with respect to y, right? You kind of always want to do the opposite there. So now that we know that we do want to integrate with respect to x, right? That means that my bounds of integration should be X values. So looking at my region here, I'm thinking about what's my smallest and what's my largest X value that are included in this region. So this one over here is going to be X equals 0. And notice that you get this point actually, right? If I was thinking about kind of the algebra side of things, this is where Y equals 0 intersects Y equals X squared. So if you were to set those equal and then solve, right, you would get X equals 0. And then this one right here is just given by X equals 2. It's the straight up and down line here. So that's how you would get those from our equations that were given to us, 0 to 2. Now, the last thing is our area formula, right? Whenever we do these volumes from, solids of rotation and all that sort of stuff, right? We may sometimes have the disk method, but we may also have the washer method. And so we need to think about, do we need to use the disk method or the washer method in this case? And it all comes down to, how does your region come up against your axis of rotation? In this case, our region doesn't butt up right against our axis of rotation. And so there is going to be an inner radius, right? And so thinking about the inner radius is going to be that smaller distance from our region to our axis of rotation. And then there's going to be a larger radius, an outer radius. And again, that's going to be from our axis of rotation, but now to the outside of our region, right? The farthest point away from our region. So quite often we were denoting this with like capital R for the outer radius, and this would be maybe a smaller r, little r for the inner radius. If you're a physicist or whatnot, you can also use subscripts, right? You can do R sub out and R sub in for inner and outer radius and all that sort of stuff. But that's going to be the last bit here, is that in order to figure out our area, right, we are going to be needing to use the washer method. And so we're going to have pi r squared minus pi little r squared. And again, we're integrating with respect to x. And so because we are still in single variable calculus, right, we need to swap out, instead of, capital R and little r, what is that worth in terms of x's, right? And so we can see actually for our capital R, this seems to be constant. That is, no matter what our x value is, whether it's x equals 0, or if it's x equals 2, or if it's x equals 1, or anything in between, right? The outer radius always seems to be the difference between y equals 5 and the outermost curve of our region is given by y equals 0. So that vertical height, that distance between y equals 0 and y equals 5, right? We just subtract in order to find that. 5 minus 0 equals 5. So this is just going to be 5 squared. Now, for our inner radius, on the other hand, right, we're not as lucky. For our inner radius, this does seem to be changing depending on what the x value is, right? It kind of starts off maybe quite large, and then kind of as our x values change and we go farther to the right, notice that the inner radius shrinks a little bit. And over here, it shrinks even more. So in this case, it really does depend on our x value. But again, the way that we find this is going to be the exact same, right? We're going to take the difference in the curves. So because we are interested in a vertical distance, right? We have our height, y equals 5 is the axis of rotation. And we're going to go ahead and subtract from it y equals x squared. Again, that's kind of what we were hitting here. That's the curve that kind of stops this inner radius. That's what's closest to our axis of rotation. Again, that was given by y equals x squared. And so if we go ahead and subtract those two y values, right, we're going to have 5 minus x squared. That's going to be our inner radius. Of course, it's never a bad idea, especially if you have a little bit of time, to be a bit paranoid, right, that we've made some mistake. And so you could plug in specific values, right? For instance, at x equals 0, this right here is suggesting that your inner radius is 5. And maybe at x equals 1, this is suggesting that our inner radius is, again, 5 minus 1 squared. So that's going to be 5 minus 1 is 4. And finally, at x equals 2, we're going to have our inner radius is going to be 5 minus 2 squared, or 5 minus 4, that's going to be 1. And you could go back and you could verify, right? So here maybe is x equals 0 on the far left. Is our inner radius, right? This purple line right here, does it have length 5? Well, yeah, because it's going from 0 all the way up to height 5. And so, yeah, the length of that would be 5. The other one that maybe we could stand a chance at seeing is, you know, here at x equals 2. At x equals 2, right, y equals x squared is going to have a height of 4. And so that distance between y equals 4 and y equals 5, right, if you subtract that, that is going to indeed give us an inner radius of 1. And so, yes, this seems to be a good setup. So maybe this is the most difficult bit of it. I see that we are after 5, so this is probably where I'm going to cut it off. But now once you have the setup, right, the integral is not bad at all, right? So these ones, I find that the most difficult thing is the setup for them. All right, let's take a few questions about this here, and then we'll call it a day. So Michael, I see your hand up first. Go ahead.
Yeah, I have my hand up from last time and I forgot to lower it. So
okay.
sorry.
No problem. Yes, then Pranav, you have the floor.
Hello, Professor.
Hi.
Hi. So, so I'm like thinking about this like exam kind of logically, right? So there we
Okay.
had 4 different sections, right? Like we had 3 exams and then the stuff afterwards. And for most prior exams, like midterms, finals that we've taken, we've like always seen like a general curve of like specific parts.
I'm
Right?
not
Finals
exactly
is always
sure.
like fair game. Yeah, so like my question is, do you feel like there's gonna be a higher presence of a certain section on an exam? Like, do you think there'll be like more
I see.
one than test 2 and like stuff like that?
Thinking back to previous years and whatnot, or previous semesters about how the final exam has been, is that you know, I think that it's typically been that there's, you know, certainly your chapter 10 style problems make an appearance, right? So I would expect to see at least one problem at very least that has, you know, your parametric stuff, and one problem at least that has your polar stuff.
Yeah.
Right. And then after that, I would say that it's a fairly decently distributed, you know, evenly across the other sections. So maybe half of the rest of it goes into the exam 1 stuff, or I guess here we have, sorry, I'm thinking about historically, there used to only be 2 exams. So I was about to say half in the exam 1, half in the exam 2. But now that we have 3 exams, that's a little bit off. But basically half of the material or so in the chapters 5 through 7, and half of the material in kind of chapter 11 and, you know, that little bit of chapter 8 maybe.
Got it. So you're thinking that like, because like we had like 4 different sections technically, so it'd be like 5, 5, 5, 5 even split, or like 5 from chapter, like 5 from the first section, 5 from like chapter 7, 5 from like chapter 10, and then like 5 from 11 and stuff.
Well, I would also remember that, you know, I mean, for instance, like 10.1, we were talking about how to parameterize curves and whatnot. A lot of chapter 10, right, you had a kind of a ramping up section, right,
like
where you didn't see any calculus, but it's like it was the algebra that you needed in order to play the game, right? Because we had never really seen before parametric curves, and we never really seen, at least in our math class, right, polar curves. And so it was a little bit of algebra that you needed in order to actually play the game. And I would put less, I mean, maybe, and if you look at kind of the old exams, sometimes they do have like, you know, some small question regarding those. But again, we're in a calculus class. And so I would put more weight in the calculus portions of chapter 10 rather than the algebra portions of chapter 10.
All right. Cool, thank you.
Yeah, of course. Let's see, how do you know how many true false multiple choice and open response questions there will be? 6 of the open response or standard response style questions, 7 multiple choice, 7 true false. Het, you have the floor.
Hello, Professor.
Hi.
I just wanted to like ask, like, if you have like any tips of how like we can tackle true and false questions? Because usually those are the ones that I usually have trouble with.
Yeah, so I agree that true false questions can often be maybe the most conceptual, right?
Yeah.
And so I would say one thing that you could do is kind of go back to where you first learned the concepts. Often this came in like the pre-class videos, right?
Right.
You can also, I mean, a lot of the web work sections have a, some true false problems at the end of them. So you could take a
Okay.
look at those. And also in our textbook, at the end of each chapter, there's a chapter review, and there's usually a true false section in each one of those chapter reviews. So if you want to see more problems, I mean, you can get those from WebWork. They usually have a true false section, or the chapter review at the end of each chapter in the textbook. But it's also possible, right, that quite often when we're making up the problems for the true false, we're again making those up from the concepts and thinking about the section. So it may not be just a copy paste sort of deal from questions in one of these two sources. So that's kind of what I would say. Maybe, if you have the time and if it overlaps with your other studying, going back to where you actually learn the concepts is probably the most useful.
Okay. Thank you.
Yeah, of course. Good. Gabriel, you have the floor.
Okay, I just had a question with the improper integral. I think it was from negative e to e of 1 over x. So
yeah,
with determining, like, this is just like a general question about like improper integrals. But like, I mean, obviously it is easy to tell if it is an improper integral when it's like, for example, like from 1 to infinity. Well, then that's like, it's easier to tell. But like, for example, like with negative e to e, sometimes it's like you can miss that it is like an improper integral. So I guess like with tackling these like kinds of problems, is it important to kind of like see what number between the two ranges it like makes the thing like discontinuous?
Yeah, exactly. And maybe what you're really hinting at here is that we need to be a little bit wary when the integral looks so simple, right? When you just have like 1 over x, like what's the likeliness that you just, integrate this as normal and, you plug in your bounds and you're on your merry way? Is that a good final exam question? Well, probably not, right? That's probably a good, if we were doing like 6.2 when we first learned about the natural log and we had 1 over x, then maybe the first web work problem could be something like that in the learning set. But that wouldn't make a very appropriate even assessment set problem or like quiz or an exam or anything like that. And so when you see something that looks on the face of it, too simple, you have to worry about, okay, well, is there a reason why this could be complicated? And then that kind of gets you thinking about improper integrals, I hope.
Okay, I understand.
Yeah, cool. Are we allowed to print out blank polar graphs to use for the exam? Yeah, so long as you show them to the camera kind of at the beginning of the exam, like your blank pieces of paper and your formula sheet. I would say I don't think it's necessary, but if it's something that you prefer, by all means, I would say that it ought to be allowed. All right. Well, thank you so much for coming, everyone. And I hope you have a great and productive weekend with your studying and everything. And I will see you guys, well, I don't know, hopefully maybe over sometime in the summer. It'd be nice to see you in person over the fall. And I hope that I can teach Calc 3 next fall. Again, there hasn't been any decision about who's teaching what next fall or next spring, but I put in that I'd like to teach Calc 3. So it'd be nice to kind of follow students throughout their calculus journey. So anyway, take care. Good luck.